Now we have our next talk from Antonio López Neumann, who will be talking about semi-simple groups. So go ahead.
Thank you, Alex. Thanks for the invitation, and thank you all for being here. So today we'll be talking about the homology of semi-simple groups. I will first say some general properties of LP cohomology before specializing to the case of semi-simple groups and say what is known in there. And then I want to advertise a result of myself regarding vanishing in degree 2 for semi-simple groups of rank at least 3. So, oh wait, oh yes. So first, what is LP cohomology? So this is something that, depending on your background, you may want to give different definitions. So there are many viewpoints for this, depending on which cohomology theory you want to work with. So if you like simplicial complexes, perhaps you like simplicial cohomology, like in Inca stock, for instance. So you can define a notion of LP cohomology in there by taking your simplicial cochains and looking at those that have finite LP norm. If you have some bounded geometry condition on your simplicial complex, your classical simplicial differential will be a bounded operator, and hence you will have a new cochain complex on which you can take the cohomology as usual. So you just define cohomology spaces as kernel on these LP cochains, quotiented by the image of these LP cochains. If you like manifolds, you can basically do the same thing. So you look at differential forms this time that have finite LP norm, though now there is a small gag because of the exterior derivative of a differential form that is LP is not necessarily LP. So you have to restrict to a smaller complex, which is the complex of LP differential forms that have differentials in LP. And now your exterior derivative will define a bounded operator, and you will be able to take the cohomology as usual. Now, I will be talking about groups today. So, well, about locally compact groups, but if you want, discrete groups can be enough, for half of the time, let's say. So for groups, you can define group cohomology. And I will be taking group cohomology with values in the right regular representation on LP. So we will focus on this one here, and this is why it requires a proper definition, which I will give now. So I want to introduce what is continuous cohomology in general. So this is something that it's the ingredients, the starting data is always a locally compact second controllable group and a continuous representation of your group on some, well, say Banach space. So in order to define a cohomology theory, you always need two things. You need cochains, you need differentials. Your cochains here will be, well, in fact, I think Elena said it right earlier. She said it right before. Well, for continuous cohomology, it's just a space of continuous maps from GK plus 1 to V that are G equivalent in the following sense. So you want to identify the action by left translation of G on GK plus 1 with the representation on your target space. Right, so these are your cochains. And then next you need differentials. So your differentials, well, it's basically the same classical simplicial differential that comes from simplicial cohomology in this continuous setting. Right, so this defines a nice bounded operator between these two Fréchet spaces. And the definition is the following. You define these continuous cohomology spaces as kernel quotiented by image, as usual. Since this space is Kerr topology, you can also define a notion of reduced cohomology. This is done by taking, instead of the image of the differential, you take the closure of the image in case the image was not closed. And the representation we're looking at today is the right regular representation on your LP functions. So LP functions, I mean LP with respect to a left Haar measure. And I will just denote it like this, like H star continuous of G with values in LP of G. And this is where we'll call continuous LP cohomology or group LP cohomology, or, well, one of those two. Right. Okay, but why do we want to consider this object? So what does LP cohomology say? What is the information it carries? First, it detects geometric amenability. So geometric amenability is just the fact, I mean, a group is geometrically amenable if you can, for a left Haar measure, you can take Fellner sets on the right. So of course, these for discrete groups are the same thing because discrete groups are unimodular. In the locally compact case, it's the same thing as being amenable and unimodular, in fact. And this is, again, the same thing as asking that the H1 LP is not Hausdorff for every P. So you can characterize being amenable and unimodular in terms of LP cohomology. This is also related to conformal dimension. So if you take a hyperbolic group, say finally generated, its first LP cohomology group is non-zero for P bigger than conformal dimension. It happens sometimes that you can make some computations using LP cohomology that can result in estimates in conformal dimension. I mean, yes, you can do computations with LP cohomology that will imply inequalities between different conformal dimensions. And well, third is, I think, a cool characterization of hyperpolicity, at least for isometric groups of homogeneous manifolds. So this is a theorem to Ponsieu saying that if you take an isometric group of a non-compact homogeneous manifold, then either your group is amenable and unimodular, in which case your first LP cohomology is not Hausdorff. Second case is your group is hyperbolic, in which case your cohomology is Hausdorff, but your first cohomology is non-zero for, I mean, your reduced first cohomology is non-zero for large P. And the third case is, if you are not in the first two cases, automatically your H1LP is 0 for every P. So it's kind of a cool theorem because the first two are, well, geometry conditions that are characterized with words. And the third one is a purely LP cohomological characterization. Now, this is a theorem that, in fact, turns out to be false in the discrete group setting, just because you can take relatively hyperbolic groups, which do not fit in the first two categories. And it is also known that they have non-zero LP cohomology for large P. Right. Now, LP cohomology also says other things. So perhaps I should have started with this. So LP cohomology is invariant by quasi-isometries. The precise statement is that if you take two locally compact second-order groups with left invariant proper metrics, if for these proper metrics they happen to be quasi-isometric, then you have continuous isomorphisms between the LP cohomologies for every P. So, and the same holds for reduced cohomology. So this tells you that you have a continuum of a priori independent quasi-isometry invariants that you can compute, that you can use to distinguish groups up to quasi-isometry. So this is something that, for instance, people have used to produce families of, produce one parameter families of groups that are pairwise not quasi-isometric, because you can compute the homology and show that there is some sort of critical exponent that moves in an interval and that shows that your groups are not quasi-isometric. Now, quasi-isometry has a measurable counterpart. I will not define this. So the measurable counterpart of quasi-isometry is what we call measure equivalence. And it happens that LP cohomology has some sort of invariance by measure equivalence, but it's a weaker statement. And so it's only known in degree 1. And what is known precisely is the following, is that if you take two finite generated groups and sub Q bigger than 1, then if your groups are LQ measure equivalent, I will not say what this is, but it's a quantified version of what it means to be measure equivalent. If you're LQ measure equivalent, then for the P's that are intermediate, so between 1 and Q, vanishing of LP cohomology on one side is equivalent to vanishing of LP cohomology on the other side. Right, so in view of all these results, it would be cool to, I don't know, like your preferred group and be able to compute its LP cohomology in order to say things like, well, is this group hyperbolic, or is it quasi-isometric to some other group? Is it measure equivalent to some other group? And well, of course, the problem is that we define a relatively hard to understand object, and there are not too many computations. So the thing is, well, we would like to take some concrete examples, like, well, semi-simple groups, and make computations in there, and well, potentially, well, afterwards. So of course, I will not do this today, but it would be cool in the future that we will be able to carry out these computations to other groups in order to say things about their quasi-geometry classes, for instance. So from now on, we will focus on semi-simple algebraic groups. If you don't like these words, it's enough to focus on SLN R, SLN of QP if you want, or products, perhaps. So perhaps the first question is what the LP cohomology of a semisimple group should look like. So Gromov asked this as a question in his second book. So he asked 3 questions on the LP cohomology of semisimple groups. The first question is, he thinks, well, so we should have vanishing of LP cohomology in degrees below the rank, and this should work for all P. The second question is, well, this should be kind of optimal. So in degree equal to the rank, there should be at least some non-vanishing. And the third question is, well, we have some non-zero vector space. It should be Hausdorff. Like, why not? Okay, so now I want to present what are the known results towards affirmative answers to these questions. So regarding question 1, what is known is, first, this is true in degree 1 for all P. This is due to Ponsonby etc. And alternatively, for simple groups, at least, you can see it using results from Bader, Neumann, Gelender, and Monod, or using La Fokker-Strong property T. Now, I put these 2 in separate categories because Ponsonby, etc. are really things that are made for working with LP cohomology and are really well suited for general semisimple groups, while Bader, Neumann, Gelender, Monod, and La Fokker are really strong rigidity properties that are, I mean, they are super different techniques, and these are techniques that cannot work for product groups, say SL2 times SL2. But if you're interested in simple groups, these other techniques are also enough. And they're also much more versatile because they work for more representations. So question 1 is true for P equal to 2. So P equal to 2 is just L2 cohomology. Of course, L2 cohomology has been studied before LP cohomology. And for semisimple groups, for real semisimple groups, this was known since the work of Borel. And for non-Archimedean semisimple groups, it was known from the works of, well, Garland, though it was not really explicit in there, and Kasselman. Now, if you want to deal with higher degree LP cohomology for P different from 2, things become a little bit more tricky. And this is where, well, results are a little bit harder to state. So in higher degrees, Boudon and Remy were able to show that question 1 is true for P in some strip close to 1 that kind of, well, gets smaller when the degree gets higher. And this is quite partial because it works for some family of simple groups. So roughly works for half. If you look at the classification of simple groups, it works for half of them. Right. So then, well, the reason I wanted to advertise is that, like, what I try to do is, well, to continue with the next degree. After degree 1, we have degree 2. So in degree 2, we're able to do it for most semisimple groups for all P. But again, there is a sacrifice in there, as it is not for all semisimple groups of rank at least 3. Right. Before continuing with question 1, let's say what is known for questions 2 and 3. So question 2, if we formulate it in this way, this is a question that is solved. So non-vanishing in degree equal to the rank is something that we know. The real case is due to Boudon and Remy. So they show non-vanishing for large values of P. And the non-Archimedean case is to myself, where we have vanishing for all P. Now I say in this formulation, the question is solved, because of course you can formulate the question 2 prime. And the question 2 prime would be, can we describe explicitly what is like the optimal P from which you have non-vanishing in degree equal to the rank, in the real case? Because this number would turn out to be a quasi-isometry invariant, because of quasi-isometry invariance of P cohomology. And it would be nice to see if it coincides with other geometric data. Well, and then question 3, well, question 3 has nearly not been considered. We know really few things about it. So I think, well, to my knowledge, we only know it for degree 1. So for hyperpoly groups, we know that the repeat cohomology is Hausdorff in degree 1. And we know that also L2 cohomology degrees below the rank is Hausdorff. But this is all of it. In general, question 3 relates to some isoparametric inequality. But it has not really been attacked in any way. Right. So now I wanted to discuss my result, which is vanishing of LP cohomology in degree 2 for semi-simple groups. So the precise statement is the following. Well, precise, I will make it more precise soon. For most semi-simple groups of rank at least 3, there is a constant, P of G, such that you have vanishing of LP cohomology in degree 2 for all P bigger than this constant. And if you're taking a non-Archimedean semi-simple group, this constant is 1. So it's basically non-vanishing. I'm sorry, basically it's vanishing for all P. In the real case, this is only for large P, though in the real case, there is also the results of Boudon and Remy, who show it for small p, and it happens in many cases, mostly likely as a coincidence, that if you join both results together, you get it vanishing for all p. Right, so now I should say what do I mean by most groups. Precisely is this list of groups. So it's all simple groups of rank at least 4, with some exceptions. So type D4 and exceptional type are exceptions. All product groups, so all semi-simple, non-simple groups of rank at least 3. Imagine SL2 times SL3. And, well, we're able to do one group of rank 3, one simple group of rank 3, which is SL4. And this is the only group of rank 3 that we're able to do with the method. And to make this statement more precise, so this constant P of G happens to be some conformal dimension of some hyperbolic space that appears in the proof. When this hyperbolic space happens to be a tree, this conformal dimension is 0. And we just set the constant to be 1. Right. So, okay, I think I went faster than I thought. So in the remaining time, I will present the proof of this result. So first, a small sketch of how the proof works from far away. So it's a proof in 3 steps with 3 different ingredients. So the first ingredient is we use an algebraic reduction. So the idea is basically that we are afraid of working with second cohomology. And the idea is using a spectral sequence to reduce the degree of the cohomology in order to work with a first cohomology group, which is kind of nicer. The problem is that a first cohomology group is nicer, but the coefficients are worse. So what we get is that we identify our second cohomology group to a first cohomology group with values in some horrible coefficients, which is precisely it's a Banach valued LP space. As a representation, it's a representation that is not isometric. It's a representation that has exponential growth. So in our book of I don't know, techniques to show vanishing of cohomology, there is like only one thing that could potentially apply, and this is Laforgue's strong property T. This is a strong rigidity property that applies to simple groups, like SL3, for instance, and that gives you vanishing of first cohomology for a large class of representations that includes some representations of exponential growth. Now, the sad part of the story is that this representation has too much exponential growth. Like it's too much to apply Laforgue. So we find I mean, we find another method, which is more of dynamical nature. And the idea is to exploit contractions in semi-simple groups. This is also kind of present in Laforgue's strong property T, but here, well, the contractions are a little bit different. And the idea is that if we have enough contractions, then we're able to show vanishing thanks to some version of Maudron's phenomenon. So Maudron's phenomenon is something quite general from semi-simple group theory. It's just a phenomenon allowing you to extend invariance of functions. And the yes, and the idea is that if we have enough contractions, we can run some version of Quanto's phenomenon. But now this is all of this is under some if. So the last part is verifying this if, so verifying the condition, and this is done through combinatorics. So what we do really is we translate the condition of being contracting as something that can be written in terms of root systems, and then we just run computations over all root systems in order to search for these contractions. And the messy list in the statement corresponds to the groups for which we are able to find these contractions. The groups that are missing in that list are the groups for which we were not able to find the contractions. Right. So more precisely, the proof works as follows. So we can describe it in the case of SLN. So in the case of SLN, the idea is to use quasi-isometric invariance to pass to a group on which we can use a spectral sequence. Don't worry, I will not say what is a spectral sequence. The idea is that we will pass to a group, a parabolic subgroup P. So in SLN, you can just take block upper triangular matrices with two blocks. So this group decomposes following what we call a Levy decomposition, MAN, where we can describe precisely what are these blocks. So the groups M and A are the block diagonal matrices. So you have 0 in the upper right coefficient. MA are the block diagonal matrices, and A is the center of these block diagonal matrices, and M is the rest, roughly. And it's essentially a product of SLNs. Then you have this group N, which is just what remains. So why do we do this? The reason is that P has a semi-direct product decomposition, and that, well, the groups G and P are quasi-isometric. So thanks to quasi-isometric invariance, we can always pass to this group P. And the second reason to do this is that when we do this, the group A semi-direct product N is hyperbolic. And the thing is, for hyperbolic groups, we can use well, lots of known results on LP cohomology that basically make the spectral sequence manageable. Otherwise, spectral sequence will just be something will not give us anything concrete. So then, how does it work? Like, the idea is you use quasi-isometric invariance, you can identify these two spaces, and then you can use this Hochschild spectral sequence to semi-direct product on P and obtain H2 of P equal to an H1 of M. This H1 of M, so here's where the ugly representation appears. But this ugly representation, you can describe what is the action in a precise way. So it has a precise formula that basically mixes some noise action, which is this thing I call pi 0, and the regular representation on LP of M. So then the goal is to show vanishing of this space. That is like the new goal. Right. So then how do we do this? The idea is to exploit contractions. So the idea is that we want to get contractions. And to get our contractions, instead of working with the semisimple group M, we pass to a smaller group that is co-compact and non-unimodular. And the main point here is that the group is non-unimodular. Well, this is fairly technical. But the idea is that non-unimodularity is a key point to produce contractions. So since this group is co-compactly contained inside of M, you can basically do all the same work as before with the group R instead of M. And once you have done that, you want to compute these operator norms, which were the obstruction to apply this Lafogue property T. And the idea is that when you work with R instead of M, there is a modular function that appears. And this modular function, well, it's a cool number because it's something that you can make as small as possible. So this operator norm, this pi 0 g, is like the bad guy of the story. This is a number that can grow exponentially fast. And the idea is that this modular function of R is something that will contract, and potentially we can produce elements that end up contracting the operator norm. So precisely, like, what do we want to do with this contraction? So roughly, what we want to do is the following thing. We want to run a version of Potter's phenomenon. So in order to state this, I need the following definition. So for some element xi in your group R, you define this subgroup P of xi, which you can think of as some sort of parabolic subgroup. And you look at the elements such that when you apply conjugation by xi minus 1, you remain bounded in the group. Now, by looking at these groups and at these contracting elements, you can formulate the following thing. So you have a vanishing criterion saying that if you have two elements that commute and whose operator norms are contracting, so I just mean that the operator norm is smaller than 1, strictly smaller than 1, and such that they are in a nice position. So nice position here means that these P of xi1 and P of xi2 generate the whole group. Then you get the vanishing. So this is roughly, this is all we want. Like, all the proof is coming to this thing. But then we have lots of hypotheses in this criterion. So the idea is that we want to verify them. And that's the last step. So the last step is, so the new goal now is to verify the hypothesis of the criterion. And this consists in searching for elements that contract the operator norm. So for this, you can use the formula that is written on the right-hand side, and you can translate each of the elements in combinatorial terms. So precisely, first, this modular function is something that classically in semi-simple group theory can be written in terms of root systems. Second, there is this operator norm that is kind of the bad guy of the story. This guy can also be written in terms of root systems. So once you have written these two guys in terms of root systems, you can basically translate this thing, this condition of this being smaller than 1 in terms of root systems, and search in which root systems this element exists. When they exist, you get the theorem. And if they don't, well, I cannot say too much. So I think this is all I wanted to say. Thank you very much.
Okay, let's thank Antonio for his talk. Are there any very quick questions for the speaker? Since we only have a few minutes left. Any quick questions? Okay, given that we have 1 minute until the next scheduled talk, I think I might just thank Antonio one more time.